So today we're going to be looking at the rank of an m by n matrix A. So we've actually already discussed the rank, we just haven't put a name to it yet. But the rank of a matrix all it is the dimension of the column space. So we talked about the dimension of the null space and the column space back in 4.5, but now we're putting a name to it. So the rank of a matrix is the dimension of the column space of A. Okay. And if you remember back from 4.5, the dimension of the column space is just the number of pivot columns that are in that matrix A. Okay, so we have this definition now, and what we want to do is we want to relate this quantity to other quantities that we know about this m by n matrix A. So the first thing I want to look at is something called the row space. So we've discussed the column space, but now I want to look at the row space. And if you remember, the column space, our initial definition for it was just the span, so the set of all linear combinations of the columns of A. In the same way, the row space of A, we'll call it row A, is the span or the set of all linear combinations of the rows of A. And we tend to denote it as row A. So in the same way as the column space of A was col A, this will be row A. So if you remember, for an m by n matrix, okay, so for an m by n matrix, it's going to have m rows and n columns. Okay. That means that the column space is going to be a subspace of Rm, and in the same way our row space is going to be a subspace of Rn, because if you look at the rows of A, each of those rows is going to have n elements in it. There are m rows, each with n elements in it. So because each of my rows has n things in it, each one is going to be an n-dimensional row vector. Okay, so each row has n entries. So row A is a subspace of Rn. And the column space was a subspace of Rm. Now, as I said, you're talking about the row space here. So it's the linear combination of the rows. But we're talking about this in terms as though it's a column, okay? We're talking about it in terms of columns, where we're saying, well, it's a subspace of Rn, which is a space of n-dimensional column vectors. And we've always said that row vectors and column vectors are not the same thing. The only thing here, because of what we are talking about, if we think about the matrix A transpose, okay, when we look at the matrix A transpose, all we are doing is making every row in A a column and every column in A a row. So we're just switching our rows and columns to make A transpose. So therefore, that means that if I were to take the column space of A transpose, I'm taking the span or the set of all linear combinations of the columns of A transpose. Well, the columns of A transpose are just the rows of A. So the column space of A transpose is just the row space of A. So I can switch this around and I can treat those rows in A as the columns of A transpose. So even though technically row space, we think about it in terms of rows, I'm going to think about it in terms of columns because I could switch this thing around to be a column space and treat them as columns, and they will work in exactly the same way. So because of this, with the row space, we do tend to write them as columns. So how do we find the row space? Well, we said the row space is the span of the rows. If we think about performing a Gauss-Jordan reduction on those rows, when we do Gauss-Jordan, all we are doing is adding and subtracting multiples of one row from another row. So what we are effectively doing to each of our rows is we are changing them by using a linear combination of the other rows. So because I am just adding and subtracting linear combinations of rows from one another, I am not changing that relationship between the rows. All I am doing is simplifying them down. So you are still going to end up with that same relationship between rows, because all you are doing is adding and subtracting multiples of one from the other. So to get the row space, what I can do is row reduce it by just taking linear combinations of one another, because linear combinations are still in the span of that row space that's still contained in it. And I'm just simplifying this thing down exactly the same as I did with the column space, where I row reduced and then just took the pivot columns. By row reducing, I'm row reducing it down, so I end up with the simplest rows possible and the simplest non-zero rows possible, so that I can minimize the amount of vectors that will be in my row space. Therefore, it will create a basis for it, because they will be linearly independent, because there will be no dependence on one another, as we've gotten rid of all of those linear combinations to simplify it down. They will be linearly independent and they will span that space. So if I can row reduce it, row reduce my matrix A, and the non-zero rows that are left are going to form a basis for the row space. Okay. What I have just talked about, where we're taking linear combinations of a matrix to get down to that row reduced version, and you get the same row space, exactly what I've just described is actually the proof for this, and I have written that down in the notes that you can read through, but it's exactly like what I've just said, so I'm not going to write it all out again, but it is in the notes for today's class. It's on page 2 of the notes for today, so you can read through that. But all it says is that by row reducing a matrix, the matrix that I end up with, the rows in that matrix, are just linear combinations of the rows that I started with, because all I've done is added and subtracted rows from one another. So the rows of my row reduced matrix are just linear combinations of the rows that I started with. Now I want to move on to the rank theorem. And there's a couple of important things within this theorem that I want to talk about. So again, we're going to take an M by N matrix A. So for an M by N matrix A. Okay, there's two things that we need to be aware of. The first thing is that the dimension of the row space is equal to the dimension of the column space. And we've already said the dimension of the column space is just the rank of A. So I can take either the dimension of the row space or the dimension of the column space, and I'm still going to end up with that rank of A. So the rank of A is actually equal to both of those quantities, and I'm going to show that that's the case in a second. But the other thing that we need to be aware of is that the rank of A plus the dimension of the null space of A is equal to the number of columns in the matrix. And I mentioned this in 4.5 when we did our last example. And I said that there was something that we had to note right at the end of that example where we were looking at the columns, and that's where this comes in. So I'm going to go through the proof of this. It's not the shortest proof, but it is kind of useful to go through a dimension argument. So the first thing that I want to look at is showing this first part here, that the dimension of the row space is actually equal to the dimension of the column space. So the dimension of the column space, as we've said before, the dimension of the column space of A is just the number of pivot columns that are in A. So when you reduce it down, you reduce this matrix down by using Gauss-Jordan, and you can see where those pivots are. So you can see where the pivot columns are, whichever columns contain pivots. So we can see the number of pivot columns that are in A is going to be the dimension of the column space, but the number of pivot columns is just equal to the number of pivots, because a pivot column is a column that contains a pivot. So this is equal to the number of pivots in A. So we know that the row space is just the span of the rows in A. Now the row space can be reduced down to get a basis for it, where we can say, okay, start out with the rows of A and row reduce this thing using Gauss-Jordan. And the non-zero rows that we end up with are going to form a basis of the row space of A. Now, the non-zero rows that I end up with in a reduced form of A, each one of those non-zero rows will contain a pivot. If you don't believe me, go back to an example that we've done in class or in the homework. But every non-zero row that you end up with in a reduced matrix is going to have a pivot in it, in either row echelon form or reduced row echelon form. Every non-zero row contains a pivot. So the number of pivots in A is equal to the number of non-zero rows in A when it is in reduced form. So in reduced row echelon form or row echelon form. It's the number of non-zero rows, I'll say, in the reduced row echelon form of A. Well, the number of non-zero rows in the reduced row echelon form of A is just the dimension of the row space, because each one of those is a basis vector for the row space. So that shows me that the dimension of the column space is equal to the dimension of the row space. So the rank of A can be described as either the dimension of the column space or the dimension of the row space. It doesn't matter which one you use because they are equal. Now I want to look at the second part of this theorem. And that says that the rank of A plus the dimension of the null space of A is equal to n. Think about what we said with the dimension of the null space of A, and we said this back in 4.5. The dimension of the null space of A is just the number of free variables in the system AX is equal to 0. So when I solve AX is equal to 0, I'm going to get my vector X, and there may be some free variables in there. And the number of free variables that I have corresponds to the dimension of the null space, because for each free variable that I have, it's going to be multiplied by a vector. And those vectors form the basis for the null space of A. So the number of free variables that I have is the dimension of the null space. Well, the number of free variables that are in this system corresponds to, each free variable corresponds to a non-pivot column in A. So we know which variables, which xi is going to be a free variable if that ith column in A does not contain a pivot. So whichever columns in A do not contain a pivot, the associated xi is therefore going to be a free variable. So the number of free variables in the system is equal to the number of non-pivot columns in A. Okay, now going back to the rank of A, as we said, it's the dimension of the column space. And again, as we've said before, the dimension of the column space is just the number of pivot columns in A. So it's the number of columns that do contain a pivot. So between the null space and this column space, when I have taken their dimensions, I've got the number of non-pivot columns in A plus the number of pivot columns in A. Well, every column is either a pivot column or a non-pivot column. It either contains a pivot or it doesn't. So if I add these two quantities together, I should get the full number of columns that are in A. So that tells me that the rank of A plus the dimension of the null space of A should be the number of columns that are in A. Okay, and that is the dimension argument. I'm going to go through an example now. So for this matrix A, it's going to be 2, 4, 6, 8, 1, 3, 0, 5, and 1, 1, 6, 3. I want to find a basis for the row space of A, the column space of A, and the null space of A. And I'm going to show that that rank theorem remains true and that it holds. So I'll show the dimension argument at the end, but I'm going to find a basis for these three things. First thing I'm going to do is put this matrix into reduced row echelon form, because that will help me with both the column space and the row space without much work whatsoever. So if I find the reduced row echelon form of my matrix A, I get this matrix. Again, if you ever get one of these on a test, always just type this into a calculator to get the reduced row echelon form. Now, you don't need to do it by hand. So I've got my reduced row echelon form of A. Now, the basis for the row space of A is just going to be the non-zero rows that I get in A by taking the reduced row echelon form of it. It's the non-zero rows, but we turn them round and put them as columns. So my row space of A has the basis 1, 0, 9, 2, 0, 1, negative 3, 1. Okay, so you just take the rows of A, the rows of the reduced row echelon form of A that are non-zero. Okay, the row space of A, you could just say that they are all linear combinations of my initial three rows. But what I have done is I've reduced it down, and we found that by reducing it down, we actually end up with a relationship between some of these rows. So you've taken linear combinations of them and reduced it down. And we know that there are actually only 2 linearly independent rows within that matrix. And we have reduced those down. So we can just take the row space, has a basis of just these 2 rows here, but we turn them around as columns. To find the column space of A, we look at the pivot columns. So this is a pivot column and this is a pivot column, because each of those contain a pivot. No other columns contain a pivot. But remember, when you do this, don't take the columns from the reduced row echelon form of A. You use that matrix to find which columns are pivot columns, but you take the columns from the initial matrix. So that tells me that these 2 columns, this column and this column, are the columns that form a basis for the column space of A. So the column space of A is just because those 2 columns are linearly independent and they span the whole column space. Now we can find the null space of A. So the null space of A, or a basis for it, is just found by solving A times X is equal to 0. So I form an augmented matrix with A and 0 and I reduce it down. So when you reduce this down, you should end up with the same reduced row echelon form matrix that you found before, with zeros that are on the right hand side. If you don't believe me, try it by yourself and you should get the same matrix, because that right hand side will never change. So all I've done is taken the reduced row echelon form of that augmented matrix to get down to here. Now when I solve this, I'm going to get x1 plus 9x3 plus 2x4 is equal to 0. And x2 minus 3x3 plus x4 is equal to 0. x3 is free and x4 is free. So because they are my 2 free variables, because I have no pivots in those columns, I can go ahead and write all of my variables in terms of those 2. So I'm going to get x1 is negative 9x3 minus 2x4. And then x2 is 3x3 minus x4. And x3 and x4 are free. So now what I can do is, using these equations, I can write my solution in terms of x3 and x4. So x is equal to, if we come back to here, I'm going to have, for x1 is negative 9x3, x2 has 3x3, x3 is just x3 itself, and x4 has no x3s in it. So I'm going to get negative 9, 3, 1, 0, plus, and for x4, x1 has got negative 2x4 in it, x2 has negative 1x4, x3 has no x4s in it, and x4 is just itself. So that's going to give me negative 2, negative 1, 0, 1. Okay. And we've said before, we know already that these 2 vectors have to be linearly independent. We proved that back when we looked at the null space. We know that they're linearly independent, and I can take any linear combination of those 2, so I can make x3 and x4 equal anything, and I'm going to end up with something in the null space. So those 2 are linearly independent and they span the null space, so they form a basis for it. So the null space of A has this basis. Okay. Now I want to look at that rank theorem again and make sure that all of our dimensions actually correspond to one another. So remember, our rank theorem said that the rank of A plus the dimension of the null space of A should equal the number of columns in A. So the rank of A is just the dimension of the column space or the dimension of the row space. And we found that our column space has 2 vectors in it and our row space has 2 vectors in it. So that corresponds to one another and tells us that the rank is 2. Now our null space has 2 vectors in it. So the dimension of the null space is 2 and that gives us 4. Let's go back to our original matrix A. We know it has 4 columns. So that rank theorem holds true, and it should do for any matrix, but we are just making sure for this particular thing that we have not done anything wrong. I would always go ahead and check your dimension arguments at the end. Now what I want to do is go back to our favourite theorem, the one that has 12 parts to it, the Invertible Matrix Theorem. Okay, and it showed us 12 things that are equivalent to A being invertible. We can now add some more parts to that, and I know that that means it's going to be an incredibly long theorem, but it's just a couple of other things to remember. So we know that when A is an invertible matrix, and again, now we are looking at a square matrix. That's a big thing to remember. So A is n by n, okay? A is an n by n invertible matrix. It has to be square. Then we know that it has to be row equivalent to the identity. So we can reduce this matrix down to the identity matrix. Okay, so it's row equivalent to the n by n identity matrix. If that is the case, how many pivots does it have? Well, we've reduced it down, and if it's row equivalent to the identity, there are going to be n ones that go down that diagonal. It's got n pivots to it. So because there are n pivots, that must mean that every single column is a pivot column. So that tells us that if every column is a pivot column, there are n pivot columns. That must mean that the dimension of the column space of A, or the rank of A, must be n. Because there are n pivots, n pivot columns, so the dimension of the column space is n, so therefore the rank of A is n. So if the rank of A is n, going back to our rank theorem here, if the rank of A is n, that must mean that the dimension of my null space must be 0 in order for this theorem to hold true. So the dimension of the null space of A must be 0, which must mean that the only thing that lands in the null space of A is that trivial solution. It's got to be that 0 subspace. So that means that the null space of A is just the 0 vector. So the 0 vector is the only thing that I can multiply by A to get back to 0. Okay, so I'm going to put this all together to give us 5 new things that we can say. Okay, number 1, we've just said that the rank of A has to equal n. The second thing I'm going to say is that the columns of A must form a basis for Rn. Okay. The reason for that is because we know that A is row equivalent to the identity. I already know that the columns of an n by n identity matrix, that's the standard basis for Rn. Okay, so if I were to take R3, taking 1, 0, 0, 0, 1, 0, 0, 0, 1, that forms a basis for R3. That is the standard basis. So we already know that we can get down to a basis for Rn, But the original matrix that you start with, if you go back to our invertible matrix theorem, you know that those columns are linearly independent, and you know that they span Rn. Okay, that's the two properties that we had, two of the 12 properties we had in that invertible matrix theorem. So if the columns are linearly independent and they span Rn, that must mean that they form a basis for Rn. So this one is actually combining two of the original properties that we had. The next thing if they form a basis for Rn, that must mean that my column space is Rn, okay? They span Rn and they're linearly independent. So my column space is literally just Rn because I can get any vector in Rn that I want by taking a linear combination of the columns of A. The fourth part that I get is that the null space of A, as we've said before, is just going to be my 0 vector because the dimension of the null space of A is equal to 0. And that's because the rank of A is equal to n. So it comes back to our rank theorem that we just did. So that's just a few extra things. Some of them are just another way of rewriting what we already knew in terms of a basis where we hadn't talked about a basis before. So we've just rewritten some of the original properties that we had. And some of the other ones are to do with the rank theorem. So we've added a few more things into that invertible matrix theorem. That is it for 4.6. We'll be doing 4.7 in the next video, and I will see you then.